fission.
If a radioactive isotope emits alpha or beta particles, they will collide with surrounding atoms. This will result in a temperature rise as heat will be generated. This heat can be harnessed to heat water into steam, which can turn a turbine to generate electricity. This is the simple version. Now let's look at it in detail to see what's going on.
Natural uranium is made up of mainly two isotopes, U-238, which is over 99%, and U-235, which is less than 1%.
If a stray neutron collides with a nucleus of U-235, it becomes very unstable. The nucleus splits into two and releases 2 to 3 more neutrons. These neutrons will then collide with more U-235 nuclei, and each of these nuclei will split, each one releasing 2 to 3 neutrons.
The reaction continues. It is a chain reaction and is called nuclear fission. If it is left to get out of control, you basically have a nuclear explosion, a massive and very fast release of thermal energy. If it is controlled, you can manage the rate of thermal energy release and use it to generate electricity.
This is not the time nor the place to explain how chain reactions can get out of control, and having checked the syllabus, we are not expecting a question like, Michael and Stephanie want to make a nuclear bomb, can you tell them what they need to do? But we are expecting questions on generating electricity using nuclear power stations, so here goes.
Nuclear fission in a power station is a controlled chain reaction.
Thermal energy, heat, is released at a steady rate.
The heat causes a temperature rise in the water supply. A heat exchanger is used to heat a separate water supply and convert that to steam. This is so that the steam can turn the turbines to generate electricity.
A heat exchanger is used because the initial water supply will be contaminated with radioactive emissions from the chain reaction. We cannot have that water passing through the turbines and into the natural water cycle.
The crucial point is the heat-producing chain is controlled.
The neutrons have to be slowed down using moderators such as water or graphite, and the rate of reaction can be controlled by adding or removing control rods made from boron or cadmium.
The process continues for 3 to 4 years, at which time the nuclear fuel has to be replaced. This can be because of the amount of radioactive isotopes has fallen, or because there is a build-up of fission products. Both of these can make the release of thermal energy too slow to be useful.
The spent fuel will be radioactive and the waste materials will also be radioactive. They cannot be returned to the environment and have to be disposed of carefully, especially as these substances can remain toxic for thousands of years.
In our next film we will look at why scientists want to build a star to solve our energy problems.
This is Science Rocks.